And what I want to get started with today is hypergeometric differential equation. That's what I want to get started with. So the importance of the hypergeometric differential equation is that it's a canonical form for some of the differential equations. If you know the solution of hypergeometric differential equation, then you already know the solution of certain differential equation. One of them happens to be Legendre differential equation or Chebyshev differential equation. So the way it is if a differential equation has three singularities, regular singular point, then those differential solutions of those differential equations are given by the hypergeometric series or hypergeometric function. That series can be identified with a function in many cases. So that's the importance of hypergeometric differential equation. And the next one we'll do is confluent hypergeometric differential equation. That is, any differential equation got two singularities. They can be represented. Their solution is just confluent hypergeometric function. Okay, so we will do these things because they capture basically many of the differential equations we are going to be coming across. So you'll see that in quantum mechanics books, they'll not say Legendre polynomial or whatever it is. Everything is represented in terms of either hypergeometric function or confluent hypergeometric function. The notations will change, but one based on the parameters, there's some parameters in the hypergeometric differential equation. The values are chosen, and the independent variable is chosen appropriately, and then you can transform the hypergeometric differential equation into Legendre differential equation or whatever, So I want to demonstrate this for you today. We'll first get the solution of the hypergeometric differential equation by the usual method, and then I'll show how based on the independent variable that you choose and the values A, B, C, we get Legendre differential equation. So that's what we are going to do today.
Could you repeat what type of singularities we would use this hypergeometric?
Yes, I'm going to do. It should have, it's a regular singular point. Of course, it cannot be essential singular point.
Okay.
So it should have at least three singular points, and I'm going to talk about that. That's the most important thing, because you have to use confluent or hypergeometric depending on the number of singularities. So basically, the differential equations are classified based on the number of singular point it exhibits. Okay, so that's what it is. That's what we're going to talk about. It's given by this particular equation, and I'll talk about other points that I was emphasizing on. Okay. So this is one thing which I have not mentioned, but I will mention here, and then we'll prove this explicitly maybe in the next class or something. So definitely x equal to 0 and x equal to 1 are singularities. I mean that you can identify. But there's also that whenever there's x equal to 0 is a singularity, x equal to infinity is also a singularity. That is what you will do is you change the variable x to something like 1 over z, okay, and try to understand how p of z, here the p of x is what it is. If p of z has a singularity at z equal to 0, that means you have a singularity at x equal to infinity. Okay, so that's how you analyze that. It's not obvious to the eye why x equal to infinity is the third singularity, but whenever there's x equal to 0 is there, x equal to infinity is also a singularity, because I can always transform the equation and try to see what happens to it. And so p of x here, of course, is c minus a plus b plus 1 times, sorry, is that, right? You know this. Q of x is nothing but AB over x times 1 minus x.
But usually we would ignore the x equal to infinity.
Because we don't expand, we're not expanding around that region, right? But so we never talked about it. Okay,
But
so it always exists. That's all I want to say.
Always exists, but we ignore because our function is not usually
We are expanding the series about a certain domain, right? So we don't talk about it.
But why here is important then?
Because that's a classification. That's how the mathematicians have classified the differential equations. Okay. So I will also collapse this next time from 3 singularities to 2 singularities. How you will go, I will talk about that. So this, what is obvious to you is x equal to 0, x equal to 1 are singularities of the differential equation. And but whenever x equal to 0 is there, x equal to infinity is also a singularity of the differential equation. And I will also do some transformation. It will become obvious when I do the Legendre differential equation. Or what we have to do is the following. You just transform this equation. Oh, sorry, I needed this in here. I'll talk about that. I was going to do separately a proof of this. You just make the transformation of variables. So x, I want to go from y of x to some other function u of z. Okay, and then wherever is dy or dx is there, you do go to d over dz or dx. You operate it on u, right? So you will transform that differential equation, and you will get a differential equation in p of z and q of z. Okay, and that will have a singularity at z equal to 0, which means x equal to infinity is also a singular point. Okay, so I'm not going to do the proof of that right now, but just to tell you where the 3 singularities are. X equal to infinity is also a singularity. Okay, so when you have 3 singularities, regular singular points, not essential, when I have to be maybe 3 regular singular points, if a differential equation has 3 singular points, then all those differential equations can be represented by the solution of the hypergeometric differential equation. Okay, so that's why Legendre differential equation comes under this category. What is it?
Hypergeometric.
Huh?
The previous equation.
Yeah, because there also we have 1 minus x squared, and I was getting confused. 1 minus x squared y double prime minus 2x y prime plus L times L plus 1 y equal to 0, right? So it has x equal to plus 1, x equal to minus 1 is there, and so this we'll talk about. We have to do the transformation in this case also. So there will be why that will come under that. I have to prove that to you actually. But so what I want you to know is that if a differential equation has 3 regular singular points, then those differential equations, the solution will be given by certain values of a, b, and c. How we can go from here to Legendre differential equation, I'll prove that to you at the end of the class today. Okay, this will go to that for certain values of a, b, c, and how you choose the independent variable. The independent variable here is x. Okay, I will make a transformation of the independent variable also. Okay, so this equation can be transformed to Legendre differential equation for certain values of a, b, c. And similarly, Chebyshev differential equation is on the one which can be represented by that. It's a confluent hypergeometric differential equation, which will cover most of our important, like Laguerre and everything will come under that, Hermite and everything.
Hermite is Hermite is not come under this.
Hermite doesn't come under this? We will check on that, okay? But Laguerre definitely comes under this. And many of the important differential equations that we come across will come under the confluent hypergeometric. Confluent, because we need to have two singularities there. Okay, so we'll talk about that next time. But what I'm going to talk about is this one this time. Okay, so although it's not obvious, there is a third singularity which is x equal to infinity. Okay, so whenever x equal to 0, there is x equal to infinity. So if any differential equation which has got three regular singular points, their solutions can be given by hypergeometric series, and those series can be represented in terms of a function which is called as hypergeometric functions. Okay, so we'll talk about all that stuff in a minute. It will become easier. I mean, do it with an example. So this is a canonical form for second order differential equations with three regular singular points. So it is based on this class. This is how the second order differential equations are sort of now classified in terms of how many singularities it exhibits, regular singular points it exhibits. Okay, okay, all right. So that is the importance of this particular differential equation. So let us go through the regular process that we normally do and quickly C minus. So A, B, C are some so A, B, C are some real numbers. Okay, so A, B, C are some real numbers. And Q of x, of course, is AB over x times 1 minus x. All right, so clearly x equal to 0 and x equal to 1 are singularities that we can identify. And of course, P of x at x equal to 0 is infinity. Q of x at x equal to 0 is also infinity. So both are regular singular points. If x times P of x at x equal to 0 is infinity. So what happens to that? If I multiply by x, that will cancel. So I'm left with C basically, right? For x equal to 0. So that is our S of Z. P of 0, as we define, is x squared times Q of x at x squared. So that is x times that, so that must be 0. Okay. So that's what we have. And the initial roots, we normally use this formula. S of 0 sigma plus T of 0 equal to 0. And so this term does not contribute. S0 is C, so what I have is sigma squared minus sigma plus C sigma equal to 0, or I have sigma plus 1 minus C to 0. Is that correct? C minus A plus B of x. So this is that, right? X times Px is, that x will cancel. So it is C. Okay. Oh, this is minus, sorry. Okay. All right, so the two roots are sigma 1 equal to 0 and sigma 2 is 1 minus C. So those are the two roots we have, right? So when I put that equal to 0, sigma 2 is 1 minus C. So those are the two roots we have. And Okay, so we keep that, and if c is not an integer and it's a real number, we can possibly get two solutions from this method. Okay. All right. So now, what do I write? My starting point. How do I start with in this case? What is y of x? What is the solution that we get started with? This is x equal to 0 is a regular singular point. So
in series terms, just means you're asking about the z sigma and
yeah, you need to get started with that, right?
Yeah.
I mean, yeah, just to making sure it's not ordinary
yeah.
it's a power series, but it's a Frobenius series. So that is nothing but an
So
x to the power of n plus sigma.
yeah.
Okay, n going from 0 to infinity. So you know the method, so you can get the solution here yourself too. Okay, y prime x is nothing but n plus sigma a sub n x to the power n plus sigma minus 1 n going from 0 to infinity. Y double prime x is nothing but n plus sigma n plus sigma minus 1 a sub n. All right, all that we have done before. So let's get the recursion relationship for this differential equation. X n plus x to the power n plus sigma minus 2 n going from 0 to infinity. We have that, and an, of course. All right, that is one term, plus c minus a plus b plus 1 times x y prime is that n plus sigma a sub n. I think I can remove all these things. All these the roots. Y prime is x to the power of n plus sigma minus 1. I have all that. So let me put the an in the front. Okay, so that's the second term. And then we have AB y, which is an x to the power of n plus sigma n is equal to 0. Okay, let's check everything is an okay, all right, an c minus a plus b plus 1 x. With that I should forget that n plus sigma. Okay, all right, everything is there. All right, let us now start collecting the terms. So I have, it's minus 1 or 1 minus, it is 1 minus, okay. All right, so I have a term which is an x, right? So that will become x to the power n plus sigma minus 1. So let me just keep them separately. So that will be x to the power n plus sigma minus 1. This will be x to the power of n plus sigma because it's x squared. And I have, this one will become x to the power of n plus sigma. So there is a term which is x to the power. So we have two types of terms coming, x to the power of n plus sigma minus 1 and x to the power of n plus sigma terms. So let us keep them separately so that okay, I need space, I'm going to write on top. So what I have is a sub n n plus sigma minus 1, okay, and that would be x to the power of n plus sigma minus 1, okay, and then I have a negative x squared a sub m n plus sigma minus 1, okay, and that is a x squared term, so it is x to the power of n plus sigma with a negative sign, I believe, okay, yeah, and okay, all that is there. Then this term will club with that one, the first one, so let me write down there, plus a sub n plus sigma a c is there, right, and then that is x to the power of n plus sigma minus 1, so it can go with that, and then this one can go with this one, so I have a negative summation n a sub n n plus sigma a plus b plus 1, right, that's x to the power of n plus sigma, right, and then this is also here, so I have one more term which is plus ab summation n a sub n x to the power of n plus sigma equal to 0. This is okay? You checked it? So now we can compare the power of x to the power of n plus sigma everyone, and so then here change a n to n plus 1, that's the term I will be looking at, right? So compare the coefficient of x to the power of n plus sigma everywhere. So that will give me what? This has to become, n has to become n plus 1. That is the term I'm looking at. The other one I can keep the way it is. Okay, sigma 1 equal to 0, sigma 2 is 1 minus c. Alright, so if I change there, I have a n plus 1, n plus 1, n plus sigma plus 1 you want, and that is n plus sigma, the second term will become, and this one will become, oh there's a c here, right, I have to worry about that, is that right, c is there, plus c n plus sigma plus 1, okay, so that will be a n, well, this is minus ABY, sorry, in the equation there's a minus A right here. So this is minus, the differential equation itself has a minus negative ABY, okay? That is my hypergeometric differential equation. I have a negative, all of them are negative. So I have this as then A sub n, n plus sigma minus 1, plus n plus sigma a plus b plus 1 plus ab. Right. So the hypergeometric differential equation is with a negative ABY. Okay, so all right. So this gives me a recursion relationship for me, and let's see what is that. So the recursion relationship that I can write is the following.
N plus sigma
Yeah, what does it separate?
It's n plus sigma a plus b minus ab.
So
Means
this
we
one,
first we take
yeah, so this is n plus sigma square minus
Yeah.
n plus sigma,
minus 1
and
plus
that
1
will cancel
yeah.
with that one, right?
So n plus
So all we have n plus sigma square, n plus sigma times a plus b plus ab, and that will factorize to n plus sigma plus a
yeah.
times n plus sigma plus b. Okay, let's just do it carefully, okay, so that everybody follows. So this one is nothing but n plus sigma square minus n plus sigma, and there is another plus n plus sigma coming, so
Okay.
they will cancel. So what I have is that is the denominator, right?
Yeah, this is the denominator. No,
That
this
is
is
the
the numerator.
So that's the numerator, yeah, numerator. So let's write down that n plus
Sigma
sigma square, okay,
minus
minus that will cancel, right?
yeah,
So just write down plus n plus sigma
a
times
plus b
a plus b, right?
minus
Plus ab, right? That's what we have on the numerator. And
No,
the
actually we have minus ab.
no, we have to
No.
put it to the other side.
It's all
All of them are negative, right? So it goes to the other side, so it becomes plus ab. So this differential equation had a negative aby. The hypergeometric differential equation is negative aby. I corrected it.
Oh.
Yeah, I made a, that's it. That's the definition of the your hypergeometric differential equation. So everything is negative, so this becomes plus. All right. Then in the denominator, what you have is okay, n plus sigma. The denominator is easy actually. N plus sigma
Plus 1.
1 times n plus sigma plus c. Yeah. N plus sigma plus c. The numerator is nothing but what? This is nothing but n plus sigma plus a times n plus sigma plus b divided by n plus sigma plus 1 n plus sigma plus c. Okay, this is your recursion relationship. It's fairly right. That is your first term, n plus sigma square. And right, then I have a times n plus sigma, right, b times n plus sigma plus ab. So you have everything there. You can just factorize it, and you can maybe do it other ways, but this is what it's factorizes to. Okay, so this is a fairly neat expression, and so let us now look at it. So what I have is the following, right? y1x, the first solution is the second solution has to be x sigma 2 an x to the power n, and going from 0 to infinity, n going from 0 to infinity. And since sigma 1 is 0, I can write this as simple as this: a naught, a1x, a2x squared, and I'm just pulling out a naught as we normally do, a1 over a0 x plus a2 over a0 x squared. Right? So we have to just get these ratios of these coefficients. So n equal to 0, I can get a1 over a0. N equal to 0, what do I get? X sigma is 0, right? A, B, over C. Okay, so I have to put this, and I'm also putting sigma 1 equal to 0. Sigma equal to sigma 1 equal to 0. That's what I'm putting in this regression relationship. And A2 over A1 is what? N equal to n equal to 1, right? So that is giving me what? A plus 1, B plus 1 divided by n equal to 1, right? So it is 2, and this is nothing but C plus 1. So A2 over A0 is nothing but the following: A times A plus 1, B times B plus 1, two factorial C times C plus 1. Okay, so that's what I need here, right? So this expression looks like A naught 1 plus AB over C times X plus A times A plus 1, B times B plus 1 divided by C times C plus 1, X squared over 2 factorial plus the nth term would be A times A plus 1. You can keep on adding this X power n factorial. Okay. Something of this nature, okay? And we choose A naught equal to 1 as usual. And so my first solution will be looking like this. And I want you to write this expression in terms of gamma function now. How to write this in terms of gamma function? There is a pattern here, right? I mean, next term is A plus 1, B plus 1, B plus 2, X cube over 3 factorial. That's what the next term will be. The third term would be that. If you just calculated A3 over A0, that's what it will look like. A times A plus 1, A plus 2, B plus 1, B plus 2, C plus 1, C plus 2, right? I'm not going to write this one because just so that you understand this one first. B plus 1, B plus 2, X cubed over 3 factorial, and so on and so forth. Have you heard of Pochhammer symbols?
What?
Pochhammer symbols. Okay, I mean, I'll also introduce that because you'll see in quantum mechanics. Some of the books will use that.
We can write by this first. We can multiply by factorial.
Yeah, I want you to write in terms of gamma functions. Yeah.
First, we can convert into n factorial terms. Then we can write gamma of n plus 1.
Okay, what is gamma of? What is gamma of A plus 1? Let's.
It's A factorial.
No. So gamma of nu plus 1 was what?
Nu is A into gamma of nu.
Nu, gamma, nu, right?
Yeah.
So what do we have? So let us say gamma of A plus 1 would be what?
It's A into gamma.
A, gamma A, right?
Yeah.
Okay, so since I've given that, I mean, similarly, gamma of B plus. So can you start thinking
Yeah.
what this will be? I want to write now y1x in a compact notation in terms of gamma function. We know the nth term. I'm just going to write the nth term, which is the easiest one. Okay? Nth term is x to the power of n over n factorial, right? It will develop into that, right? That's clear. But I want now all these things these factors which are coming to write in terms of gamma function.
We can multiply by a minus 1 factorial above and a minus 1 factorial down, then it converts to a plus 2 factorial. And
I want to write in terms of gamma of a
Gamma.
plus n and gamma
A
of
plus.
b plus n
Exactly.
and all that stuff, okay?
That's it's going to be gamma of a plus n.
And what is the denominator then? See, I want you to look at this, right? I mean, gamma of a plus 2 is what? Gamma of
A plus 1.
a plus 1 plus 1, okay? Which is nothing but a plus 1 gamma of a plus 1, right? I mean, that
Yes.
you can see.
And it's a and gamma s.
So I want this to be written in terms of this whole thing, like each here it is a, the other one is a times a plus 1, the next one is a times a plus 2. So let us first,
Is it factorial? technically?
I want to write in terms of gamma function. I'm not even,
Well,
I want you to just use this property, that's all at this point.
Well, I mean, it's the multiple of the prior step, so I figured a gamma or a factorial would work.
I mean, this is also factorial. Eventually it is a factorial, right? I mean, new factorial. I mean, but I just want you to write in terms of,
yeah, then it will cancel out.
But you have to like divide it by gamma.
so
No,
there's something I want you,
Yeah.
this, it's not going to work directly. There's something you have to do to get the first term. Don't look at the first term because there's a problem there, okay? I mean, you have to do something to get one, okay? Look at the second term or third term, what would work? I mean, what should I write in terms of gamma function for a times a plus 1? The last term is a plus, I think second n minus 1 perhaps, right? I mean,
I think it's the gamma of a plus 2 upon gamma of a.
that's not correct because n we have to have, it keeps on changing, it's not 2, right? Because it is a times a plus 1, a plus 2 is going on. The fourth term, a plus 1, a plus 2, a plus 3 is there, okay?
So gamma of a
Yeah,
parentheses a plus n.
correct, yeah. So that will be the first term, okay?
Okay,
And what about b times b plus 1, b plus 2? Write it in terms of gamma function,
it's the same thing.
okay? But with a b, okay? And let's check whether it works. And the denominator is developing like that, right?
Gamma of c.
So can I write it like this?
Yes.
Exactly.
Okay. Now, but
you have to
is it now? We have to do something. This is not still sufficient. Okay, that's what I want to say. What is n equal to 0? N equal to 0. According to this, it is
Okay.
gamma a, gamma b,
Exactly.
gamma.
You have to
C.
divide it by.
So when c is equal to 8, the
N equal to
product of
0,
AB,
I need to have another multiplication factor. Okay, so just let's. So this is nothing but gamma of c over gamma a. I have to multiply this by prefactor like that. Okay, so this expression becomes that. Is this clear? Right? N equal to 1, we can check. N equal to 1 is. I need to get this n equal to 1, right? I mean.
Okay.
So that will be what? Gamma of, second term gamma of this, gamma of b plus 1, gamma of c plus 1, okay? So this is nothing but a times gamma of a, and this one is b times gamma of b, and the last one is c times gamma of c, right? And I need a, b over c, that's all I need. I need this, I need that, I need that. So I'm just trying to reverse, multiply by gamma c or gamma a times gamma b, so that becomes ab over c. So that's why I have that prefactor. In order for this to become that, I need to put this prefactor, which is the inverse of that. Okay, so that is a compact notation for the series that you're getting, the solution of this hypergeometric differential equation. And so basically, for a naught equal to 1, this is the series which is called as hypergeometric, written in this notation. This is a hypergeometric series. It's nothing but, so it's a pattern is emerging, right? It is A, B, and C, AB over C, and the next term is nothing but A times A plus 1, B times B plus 1, divided by C times C plus 1, x squared over 2 factorial. So this infinite series is what is called as hypergeometric series, and if the series becomes a function, that's called as hypergeometric function. Okay. So that is your first solution. I mean, that is in the compact notation I've written. Is this clear? Okay. All right. Now, there's another notation that I want to introduce because you may see it, you may come across that in some of the quantum mechanics books. So that is the Pochhammer symbol that I want to introduce also in case. It looks like, factorial, but it is not ending in 1, so that's why I want you to be. The Pochhammer symbol is like this. A, with the suffix nu you write, is nothing but it starts like A times A plus 1, A plus 2, all the way to A plus nu minus 1. Okay. So factorials will end in 1, right? It doesn't. So that is the, in some sense, all these things could be, this is A of A1, right? I mean, yeah, so n equal to 1, yeah. So this is, this part is only A1 in some sense, B1, right? I mean, so this whole thing could be written in a compact notation of A nu, B nu over C nu, right? I mean, so you may see it in that notation in terms, instead of gamma function also, okay? So that is another way of looking at it. So basically, this is your A2 term, B2, C2 kind of a thing. So that is another way of writing it, I think. You may say it that way. Then that's nothing but this guy Pochhammer introduced a shorthand notation for this kind of a term. Okay, that's all it is. All right. Now, what is y2x then? Oh, wait. Sigma 2 was 1 minus c, right? What happened?
No, I was just saying.
I need that recursion relation. I erased it. So that is the recursion relationship in a general form we got. And I can substitute sigma equal to 1 minus c to get the a1 over a0 and all that stuff. It looks messy, but I'll tell you how to get the result in a very simple form. So this is a0, 1 plus a1 over a0 x, a2 over a0 x squared, and so on and so forth, right? And we will take a0 equal to 1 as usual. Let's take that constant as 1. All right. What was the relationship we got? Previously, I want to go from there. For sigma equal to 0, let me see if I have it. Okay, let's write this and then I'll come back to that. I'm just, I need to make some analogy and then get it quickly, the result, rather than getting all those coefficients. So this looks like n plus a plus 1 minus c. The other one is n plus b plus 1 minus c. I'm just substituting for sigma equal to 1 minus c at this point, that's all. N plus 1 minus c, so this becomes 2 minus c, this term. This is nothing but n plus 1 because 1 minus c plus c will cancel. So this is the recursion relationship for sigma 2 equal to 1 minus c. All right. For sigma equal to 0, what we had was the following.
Professor,
Yeah.
if c, what if c is integer?
What?
If c takes some integer value.
Yeah, then there will be an, that's why I said c is a real number which is not an integer at this point, okay? So c equal to integer, there may be an issue in some situation. You are going to be having a issue because it could cancel. That series may cancel, I mean, you know, it will become 0, the denominator could become 0, right? So yes, that's why I put c is a real number which is not an integer at this point, okay? Yeah. Okay, where are we? Okay, I need this. Okay. For sigma equal to 0, we had this relationship, right? N plus a, n plus b,
n minus n plus 1.
n plus 1, and n plus c. This is what we had, right? Now, so this is what we have here, and for sigma equal to 0, this is my relationship. This is my y1x. Okay, so I want to, instead of I can calculate a1, a2 and all this, you know, we have to factorize quite a bit and all that. So I want to give an answer, you know, without going through all the algebra. Okay, so that's what I'm trying to do. So y2x, definitely I have that term, x to the power 1 minus c is there. And then times, I have some series, okay? Now, I want to guess this series without actually calculating a1 over a0 and a2 over a0, right, for this case. Which you can do, but I just want to see what is the difference, right, between these two relationships. I have n plus a. A has become somehow a plus 1 minus c. Okay, b has become b plus 1 minus c. C has become 2 minus c. Other term is there. So if I replaced everywhere with a by, this is what you should get if you did the full calculation too. Okay, a plus 1 minus c. B is this. C. C is 2 minus z. And x. Okay, so basically in this equation, that's what has happened, and the next one is just adding by 1, I think. So that should be okay. This is a, so a plus 1, so you will have a plus 1 minus c, a plus 2 minus c, and so on and so forth. B is b plus 1 minus c, b plus 2 minus c. This will be c plus 1, right? So that will be 3 minus 1 x square over 2 factorial. Something like this, okay? You can check that explicitly, you have it, so you can do it explicitly and get that all that stuff. Now this y2x, now if I had to write it in terms of this hypergeometric function, the notation that people use is the following. I have to just change, my second solution is nothing but a has become a plus 1 minus c. So people will say that is the second solution without even doing the full thing. 2 minus c, okay, x times, of course, I have that x minus. This is there, right? Because this term, x for sigma term is there, right? Which is, because sigma in this case is, sigma 2 is 1 minus c, so that is the plus this. You can write your second solution as the following. All right. So the most general solution, of course, is a combination of that. So a times f a b c x plus b x for 1 minus c f of a plus 1 minus c b plus 1 minus c 2 minus c. Okay, so that will be the most general solution. Depending on the value of c, you know, in a realistic problem, you can put one of the coefficient 0 if one of them is blowing up. You can, you know, that's how it'll, you know, if it is if c becomes an integer, then you can say, okay, that may not be realistic. You know, one of them will not, because I think it has got c plus 1 and all that. So, so you know, if that series becomes, make that as, you know, b, the coefficient b, you can make it as 0. That's how it is, say that's an unrealistic solution. Okay, so that is your f is your hypergeometric function or series. So based on the value of a, b, and c in your hypergeometric differential equation, they will transform to a particular function. Okay, Legendre polynomial or even simple things like exponential or whatever it is, it can become. Okay, so this series that we see, I'll just write down for some and I'll prove it for the Legendre polynomial. All right, so this is what I'm going to prove for you, but if a was m plus 1, b was negative m, c was 1, and let me just call it 1 minus z over 2, is this is nothing but I have something like this. I'm also changing the independent variable from x to 1 minus z over 2 in this case. Then that becomes Legendre polynomial. Okay. B and C are the same in this case. That is nothing but 1 minus x to the power of minus 8. So in this case, the infinite series has become a function. Okay, so some simple function it has become. Okay, so then in those cases, these are called as hypergeometric functions rather than series, right? I mean, if you can get that. We never did Chebyshev polynomials like Legendre, except I think the second term has a different coefficient. That's also because it's like Legendre polynomial, so that also comes under this category. F m minus n half 1 minus x over 2. That gives you the Chebyshev differential equation, and the polynomial is called Chebyshev polynomial. Okay, this is Legendre polynomial that we have done. Okay, I just want to give you that. I think Chebyshev is just 1 minus x y double prime minus x y prime rather than 2x. That's the only difference as far as I know. 1 minus x squared y double prime minus x y prime plus, did I put m here? Okay. I think m y equal to 0. That is Chebyshev polynomial. In Legendre, you have exactly the differential, the second term, right? I mean, whereas here it is minus x. So it looks, similar. Well, it's not quite the same, but it is, somewhat of that category. So that is your Chebyshev differential equation. Many times when you are fitting a curve, you fit with Chebyshev polynomials. Okay, it's one of the, for curve fitting, you may use that sometimes. Okay. All right, let's understand this. Why is this Legendre polynomial, right? I mean, so where is our differential equation? All right. I'm going to leave that. I need that. All right, so our differential equation, the hypergeometric differential equation is x 1 minus x y double prime plus c minus a plus b plus 1 x y prime. Here it is plus a b y. Plus or minus, this is where I made a mistake previously. Is it plus minus? Is minus? Yeah, I know, that's where it's negative, right. Negative ABY, okay, that's C minus A plus B plus 1x, Alright, so what I want, we know the solution of this is something of this nature, F, A, B, C, X, okay, that's the solution of that differential equation. Y1x is something of that nature. Now, so what is A? If I have to prove this is Legendre polynomial, the first thing is what is A there? I mean, I have to.
M plus.
A is.
M plus 1.
A is m plus 1, right? B is.
Minus M.
Negative 1. Okay,
C is 1.
C is 1. Okay, at least we know that. And then my independent variable is 1 minus z over 2, right? So what I have is, I have to map y of x, I have to convert this into independent variable z, right? So all these are going to be d square y u over dz square and all that. So y becomes that. So this is the transformation I'm trying to make. So what is d over dx becomes what?
Minus 1 by 2.
Can I
Yeah.
dz over dx? Let us see if that is what I have to do. So if I make x as 1 minus z over 2, okay? If that is dx is then negative half dz, okay? So then this operates on y, this has to operate on u because u is a function of z, right? So this is nothing but, so y prime of x transforms to negative dz over dx is negative 2, right? So negative 2 of u prime of z. Okay. This is a straight map, yx, whatever it is, you have to substitute by 1 minus x over 2 directly. Y prime of x, y double prime of x maps to what? What is the factor I should put? U double z. This is negative 2, right? I mean, this is negative 2. This becomes negative 2, this. So I want to know what is d square over dx square. What does that become? Can I write it as a 4 times?
Yeah.
Is this correct? Right? Okay, so that becomes this. Okay, so all I have to do is now I've changed the independent variable and I have to, for x I can put 1 minus z over 2 and see what happens to that differential equation because it has to become your Legendre differential equation. Okay, so that's what. So x is 1 minus, okay, here, now x has become 1 minus z over 2 based on, this is what we want to check, right? So 1 minus z over 2, 1 minus x becomes what? X is 1 minus z over 2. Can I write it as 1 plus z over 2? Why? This one is what? 4 times e this plus c minus a. A is now let's start substituting for everything now. C is 1 minus a is m plus 1, b is negative 1 plus 1 and x is
B is negative m.
yeah,
Okay.
1 minus z over 2, okay. Y prime has now become negative 2. Y prime is negative 2 over, so this will become plus, I think, plus 2 u prime, okay. Got everything now?
The first term will be negative.
Okay. Let me just check in a minute, okay? Plus, what's the last name? Minus ABY. AB is
M to m
plus m times m plus 1 times u equal to 0. Alright, let me just check. C is 1, okay, so that's what that is. For a minute, forget that. A is m plus 1, B is minus m, C is plus 1, and X is
1 minus z by 2.
X is 1 minus z over 2. This is part of that. And u prime, okay, let me just see where is that? Oh yeah, u prime is,
2u.
okay, so that is outside. Okay,
Yeah.
2 is outside. So 2u is, 2 is here. Okay.
Negative.
Negative, and
Yeah.
this is negative, so it's plus. Sorry.
First
Oh,
time
this
is
is
one,
negative.
yeah.
Yeah, this is negative. Yeah. Okay. So this is negative. U prime, y prime is negative 2u prime. It's
But
negative 2u
inside
prime.
is minus.
Huh?
1 minus.
Where is 1 minus here?
No, this first minus 2, 1 minus, I think.
So sorry. Let's go. This is what I'm trying to translate. Right. C is 1.
Yeah. Here is minus.
There is a minus
Yeah.
sign here.
Yeah, now it's correct.
Minus A is m plus 1, negative m plus 1.
Now it's correct.
Yeah, okay, yeah, I was thinking of that negative sign because I put it, yeah.
It's
Yeah,
all-
well, but now it's fine, right? I mean,
Yeah.
X is there, okay, everything is there. All right,
Everything cancel.
yeah, so what is happening is m and m will cancel.
2 cancel.
Uh,
2 is also cancelled.
One
And then
by
1
Z.
minus
this
One
2
minus
is
A.
cancelling with
Yeah.
that 2,
and
right?
simply 2z.
So I have
And then 1 minus z. There
1 minus
is
s
also
plus, so this is nothing but 2z, right? This
Yeah.
whole thing has become nothing but
2z.
this has become z, so this has become negative 2z, right?
Yeah. Yeah.
Yeah, that negative sign and that negative sign goes away, so that is just z. This
Minus
whole-
2z. Full.
Yeah, with all that will be negative 2z. Okay, so what you have is so and this will cancel, so it's nothing but 1 minus z square u double prime negative 2z u prime plus m times m plus 1 u equal to 0, which is your Legendre differential equation. Okay. Okay, so all I've done is substitute C. A was m plus 1, B was negative 1, and X was 1 minus Z over 2, and then Y prime is negative 2U prime. Okay, you have to operate on this, right? Why? This is nothing but, this will become minus 2U prime. Okay. And this one, when you operate on y, becomes plus 4u double prime. Okay, so that negative is coming because of y prime is nothing but negative 2u prime. Okay, so that's where that negative sign is coming. Okay, so I could have put it here, and I may have changed sign also. You could have put a plus and minus 2u prime, but I took it over there. So that's what is happening. Okay, so this is negative 2u prime, so that is a negative sign coming. 2 is there coming from there, and this is 2, and that 2 will cancel with that, and this one will cancel with that, and that will become 2z. Okay, so basically, so the whole task is to find what are the values of a, b, and c in the hypergeometric function series that will give this. Now remember that we had Legendre polynomial when we did the series. Now you can write the solution because it's very easy to remember the hypergeometric function series, right? Because 1 plus ab over c is times x, right? That's a term. So and abc, you can write the solution now fairly easily because it is simply the solution will be 1 plus what? AB over C times X, A times. So it's easy for us to write. Maybe 1, A is, so basically negative M times M plus 1, and C is 1, so I don't have to do anything. So the leading term, you already know how it is. So I'm just trying to say it's easy for you to write because ABC, you can write a few series. So so once you know the hypergeometric, the only thing you have to eventually remember is the hypergeometric series form, and similarly for the constraint hypergeometric series form. And if you are given all these things, you write the solution in the series form or whatever it is, you can write down easily. So that's the advantage, or let's say why people have come up with this try to classify all the differential equations based on singularities, then at least you can write.
But here in singularities you consider infinity also.
Yes,
Yeah, but-
that is based on similar transformation you have to do. Yes, you have to yes, they have, when they say 3 singularities, they have considered infinity. Yes, x equal to infinity.
No, but infinity is not a regular singular point.
Whenever x equal to 0,
Yeah.
it will have, x equal to infinity is considered as part of the singularity even for your hypergeometry differential equation.
And you said that it is removable by doing transformation.
This equation, for instance, when you write this, x equal to 0 and x equal to 1
Are singularities.
singularity because of p of x. But x equal to infinity, if you just look at the differential equation itself, this differential equation doesn't exist for x equal to infinity because it's in the numerator. It will not have a solution at x equal to infinity. So in that sense, it is a singular point.
Okay.
So the way they classify is how many singular points this
Okay.
differential equation has. Okay.
In general, they consider all the points on which this differential equation is not.
It doesn't work. Exist. Yeah, exactly. For which you cannot find the solution. Basically, yeah, that's what it is. Yeah. So the classification, somehow, they found this way of they can put some of the differential in a certain type, and you can find the solutions. Knowing the solution of that differential equation, that's all it is. I mean, it's a way of mathematicians' mind work of classifying, and they feel these types of differential equation may be classified as hypergeometric differential equation can now be considered as a canonical form for certain types of second order differential equation. Once you know the solution of that, you can get the solutions of the others without explicitly deriving it, which you can do, but that's what they are trying to capture here.
So what kind of second order differential equation would we not be able to solve for?
Where you cannot solve for, if p of x and q of x are not removable singularity, you cannot solve it, right? If xpx, let us say you have
If it has some range from -1 to...
No, more than that, function form, right? If you have p of x had 1 over, something x cubed, let's say, times something, okay? You cannot remove it, right? If you had some differential equation, you just cooked up, let's say, y double prime plus 1 over x cube y prime, it will not work. I mean, so, yeah.
But in starting, you just write x equal to infinity as a regular singular point. It should be essential.
It is not essential. It is called ordered singular point, actually, because somehow the way they're trying to say the fact that it exists is not, if you think of p of x, the way we defined is through p of x, right?
Yeah.
I mean, but if I just look at the differential equation, I know it cannot, x equal to infinity, it is not.
But it is not also removable.
It is not, the removal singularity is always exponential of 1 over, removal, all these things are based on p of x.
Okay.
So what I'm trying to say is, this differential equation,
You
if you
define
look-
based on the differential equation directly, not based on the px and qx.
not only that, what, I can always transform, any differential equation I can transform, right? Nobody can say, I can change of variables, I can do it any time, right?
Yeah.
So the only way we can understand even the number of, the problem is how to count the number of singularities,
Yeah.
right? Yeah. The number of singularities, the way they count is not only by looking at it, but also making a transformation of that differential equation, the independent variable. And the simple, for x equal to 0, one of the transformation is, look at, instead of x, let me put 1 over z, x equal to 1 over z. And you look at, instead of p of x, p of omega. Now the differential equation, the way I have done, now you can, I will illustrate it maybe next time for Chebyshev or something like that, so that you do understand why they are calling the other one is also a singularity, because so x equal to z, it is not obvious. I understand it is not obvious because all are the way the Frobenius series method has worked is through analyzing p of x and q of x. So they're not only now saying analyze p of x and q of x, you also have to now analyze for p of z and q of z, where z is 1 over x. Okay,
Means some
and how does that
transformation.
differential equation, given this differential equation, let us also transform the independent variable from x to 1 over z, or whatever, 1 over omega, whatever it is. Change the variable to something like this. And if p of z also exhibits a singularity, they are counting that as part of the number of singularities. Yeah, it is not only they're looking at p of x the way we are able to see it, but it sort of intuitively I can understand x equal to infinity. This equation doesn't exist, but the way they prove it is, let's do the change of variables instead of y prime, which is dy or dx. Let me also, the independent variable is not x, but now it's 1 over z. And for z equal to 0, then I modify the whole differential equation and I examine p of z. Okay, and it does p of z now for z equal to 0 become infinity. If it becomes infinity, then
Okay.
it is the other way around, because anytime I can change a variable is not, we can do it. Okay.
Then it becomes z equal to
Yeah.
0 as a regular singularity.
Yeah. So it is a funny way of counting the singularity point, because it's not
Yeah.
obvious. That's why I never said in the beginning of the lecture that there is always under one. But it becomes relevant for classifying this second order differential
But,
equations.
But how we can know how many transformation means? Here it's obvious, 1 upon z is obvious.
Yeah.
But is there any example there where we means
There may be
start that to find how many transformations exist such that there will be many more singularities? Is there any way to
see.
count?
Okay. All right. We are also looking always at I know it may be very difficult, right?
Yeah.
But x equal to 0, I know there's always under
Yeah.
x. That is the case. They always say there's under one exists. Okay, so that is the case. But there may be, what you're saying is, can I do other transformations where?
It means suppose somehow there is a x minus 2 or something like in denominator, then somehow there is a transformation that some other points also exhibits singularities. But
Right. I understand your question.
But is there any method to check that how many means?
How to count the the counting of the singularities is a difficult issue. It looks like, it's not that obvious how to count it, but all they say is x equal to 0. That is the most obvious case.
Yeah.
Corresponding to that, there is definitely one at x equal to infinity. Corresponding to x equal to 1, is there under singularity? That's they have not, definitely in the books they have not defined it. It looks, it doesn't exist, but
Yeah.
I don't see the proof of it. Is there a transformation? Because why?
Yeah, suppose here is x equal to 1
Yeah.
is also singularity, but
Yeah.
no, so x equal to 1 minus c or for some c there is some another singularity, but if we do some other transformations so that there is one more singularity.
Right. It looks, it doesn't exist based on the way it is, because I don't think they have just said for this equation there's only 3 singularities. It doesn't have.
There must be a proof.
There must be some proof. The mathematicians are very, very rigorous in terms of their.
Yeah, because they
it
say,
is not obvious. Yeah.
If they say 3 singularities, then they.
Yeah, they have done by other means. But I understand. Is there any? If I, for the other case, I make the transformation, whatever it is, 1 over z minus 2 or something, and then does it have,
Singularity.
at z equal to, yeah. So, but the transformation is going to be a little bit complicated. But who knows? Yes, it is not. The proof is not the counting of the number of singularity. The proof is not that trivial. Definitely x equal to 0 is the easiest one because you can do the transformation like that, and then you can check it. But others are not easy to do, and I think. But I think there must be definitely a much more rigorous proof of that. Mathematicians will not, they are more rigorous than physicists in that sense, right? They do it. So yeah, so that's why I never said initially, in the beginning there are three singularities. I never said when I did the Legendre differential equations, but we will look at it at least, one transformation we'll do and check indeed, P of W or P of Z. If you do the transformation, indeed it has a singularity. So that way you are convinced why it is, right? I mean, so for x equal to 0 we can convince, but I cannot say, corresponding to x equal to 1, is there any other transformation that,
Exist,
yeah, that's I don't think I can prove that. I don't know the proof for that, okay, how to do it, but I'm just going to take it.
For
This
the
is
next confluent hypergeometric, there should be only two singularities.
I will tell you how we do. That's also very neat. I will collapse the three singularities of this to 2 actually. One of them I'll make it go to, it disappears, okay. So I will collapse this. I will not even prove that from scratch, the proof, the solutions of this. How do we collapse 3 singularities to 2 singularities? And that will give, from here I will get the confluent hypergeometric differential equation by collapsing the number of singularities from 3 to 2. Okay, so that's what I'm going to do. So that may also give us something, but some idea of it. But I'm pretty sure there's more rigorous proof. Why, is there under one corresponding to that? Anywhere, I don't know, because we can try, but I maybe it is, I don't think the proof is trivial. That's what my hunch is. I mean, it's not trivial. Yes.
So here we plugged in for y1 of x, we substituted n plus 1, negative m1, and for abc.
Mm-hmm.
What's the significance of the meaning of y2 of x? What would happen if we plugged in there? Does that give us the
What?
infinite series that we
What-
found
which-
when we solved Legendre?
What did you say? I don't get the point.
So
Yeah.
here we plugged into y1 of x,
Yeah.
but what about y2 of x from when we solved the hypergeometric differential equation?
Oh, I see. Okay. So what you're saying is, what about the second solution, right?
Yes.
Yeah.
Why did we choose y1 of x? And is it just easier, or?
No. Only that one gives the Legendre polynomial. If you
Yeah.
do the corresponding, it may give us some other function.
Does that function correspond to, when we solved the Legendre differential equation originally, we had the polynomials that we had an infinite series. Would solving y2 of x this way give us that infinite series that we had found originally?
No, see, everything has two solutions, right? I mean, if m is not an integer for a minute, let us say, okay, then we do have PL and P minus L are two different solutions, okay? We do have, even Legendre differential equation, we got two solutions, PLX and P minus LX, right? I mean, so probably that gives you P minus LX, that series rather than Legendre polynomial. That's a different series. We have two solutions, right? Even for Legendre polynomial.
There's a constant times the polynomial plus and then an infinite series.
Yeah, means
Yeah.
it's a alternating
Right,
polynomial, infinite, then put the y2x is polynomial, then infinite, then we combine, then we got the polynomials.
No, that's right. I mean, like we got polynomial and infinite, the two solutions,
Yes.
right? Depending on L is order
Yeah,
or
L
what.
is
So
order.
here when we substitute
Yeah.
in a y1 of x, we get Legendre differential equation? I mean, what happens if we go into y2 of x? Is it just some random function, or does that have any significance for Legendre differential equation?
The second solution you're asking, right? I mean, we can try. I mean, we can do it.
Yeah.
What you're asking is, if
F of a minus
what does that?
a minus 1.
What was that? A1.
A 1 minus c. A minus 1 plus c. I think. 1 minus c. Plus 1 minus c.
Plus 1 minus c,
Yeah.
right? Yeah. What was that one? 2 minus c, right?
2 minus c.
Let's call that. Okay, that is my second solution, right? I mean, also I have this, right? So we also have this in this case, right? I mean, that's my y2x here. This is my second solution here. So your question is, what does this become, right? I mean,
Yeah.
I mean, is it leading to, if you had put, let us say, some of these things, okay?
Does that have any significance, or is that just?
They're the same because for A you still have m plus 1 because now you have.
No, we don't know. Those are things some people have tried, right? These are not
Yeah.
that obvious. They have tried many times. What I mean, we are just using it. Which somebody has tried many times. What should A, B, C should be? So I feel this has to be attempted then for different values of A, B, and
Yeah.
C to see what it becomes. That series that we have, because we at least know what the series is, right? I mean that we know. A plus 1 minus C. This at least, let us say, I mean, first couple of terms we did AB over C, was it? Yeah, AB over, what was that? Over C, right?
Yes,
minus
with
C.
2 minus.
2 minus C.
Might be it become some other series, but we
Yeah.
ignore it because
No.
we need legendaries.
Right, I mean, it may or may not even give you the
It just
Y2
may.
of Legendre.
So the m plus 1 negative m.
It's very strict, it's connected, they are connected only to the Legendre polynomial, not to the other series because,
Right.
yeah.
But they tested, whoever the mathematician was that was testing, is only tested for y1 of x.
Y1 of X, yeah.
But for
Yeah.
this case we have
But-
y1 equal y2, so it doesn't matter which. This case we have y1 equal y2.
It is not. It's
Because
not.
if you plug in A equal m equal 1 and then C equal 1, then you have the first like real number is still m plus 1, which is
What are you saying? I mean, if you substitute A could M plus 1,
yes.
yeah.
Then it's m plus
Then,
2 minus C.
Then here you have m plus 1
Yeah.
plus 1 minus 1 because C equal 1, and you still have 1 equal m equal.
M plus
A,
1
the
minus
first
C.
It's like it's similar to this case where you have A equal m plus 1.
Yeah.
So I mean you have y1 equal y2, so it
Yeah, it's
doesn't matter
similar.
which solution you plug in.
But then, but you also, the second solution, you also have this. X
C
equal
is
1
equals
minus
to
C.
1,
C
that
equal
goes to
1,
0.
so here you
Huh?
have x
That
to
goes
the
to
power
1.
of 0.
Or X equals 0, that
Yeah.
also
That
becomes
becomes both the solutions will become same.
same in this case, I see. Yeah, in this case it becomes, yeah. Yeah, but I feel it has to be played with,
Yeah, that's how they choose A, B, C, and that's how they.
yeah, you
goes
have to
1
play
minus
with the parameters. In this case, it looks like they are the same, but
C. Maybe we can try this, the another. If both are same, then it's.
but what about everywhere it becomes the same, right? The
Yeah.
next term is also
Yeah.
cancels symmetrically. I mean, this is only the first term.
Yeah, it's a symmetric case.
A times A plus 1, that also becomes everything.
Yeah.
So, okay. So somebody has, that means has tried everything. So, okay, I mean, so it is, regardless, it looks like whether this or that
You plug in this.
is giving Legendre polynomial. That's not in your summarize of different functions. They don't even talk about the other one. It only the A, B, C. That's the only thing they talk about. But even this, you know, it is a lot of work. I mean, even to think about this variable, you know, why should that be the independent variable? It's not it is, you know, by itself a research topic, I would say, you know, to you know, even say this is what it is. I mean, but I feel it has got a more deeper, the whole thing in this, not even this thing, is the fact that they identified that singularity is the most critical. The number of singularities is a critical way to classify, is a more deeper, you know, deeper discovery, I would say, than even this. This is at least a trivial, you know, you have to try many attempts. But the fact that they identify it is the nature of number of singularities that we count, you know, classifies the differential equation. I think that's a much deeper research work, whoever did it. I mean, in my view, then this at least we can attempt many things. You know,
This is just like a hit and try.
hit and trial, but you know, maybe after some time you get the hang of it, you know what it is. But the fact that, you know, it is even from there, and they got that differential, but then they say it is, you know, it's based on the number of singularities.
Yeah.
I think that's a much deeper discovery in my
Prove that only for any number of transformation only there will be 3 singularities for this.
Yeah, I think that's, I mean, how they hit upon that, I have no idea. Yeah.
But I looked into it, and
Mm.
Bessel function has 2 regular singularity points, like, and we can approach, like, we can get Bessel function from
Bessel has what, x square, it starts with x, right? X square, right?
0 and x infinite.
Zero and infinity, yeah,
exactly.
okay, yeah,
But-
yeah.
but-
So that will not, cannot come from here, it should come from the confluent hypergeometric differential equation in that
Yeah.
case.
Yeah, it's a limiting factor. There is a limiting factor, and we can like get to there.
No,
like,
but
from-
the question is that how can you prove that for any number of transformation there will be only 2 singularities?
yeah.
Yeah, I mean, so there is some other proof here going on here, yeah. So, even Bessel is a little bit easier, but this one, why would are there other transformations? We don't know. I mean, that they can.
Yeah, in Bessel, because x equal to 0 is only
Yeah, there it is a little bit easier.
Yeah,
Not
but
in-
here is x minus 1 minus x.
Yeah, exactly. Yeah,
that's
yeah,
why there's-
yeah. So to say that it's not trivial, I don't think so. Yeah. So there must be other proofs for that, actually. Yeah. Okay, so next time what we'll do is confluent hypergeometric differential equation, and then I will. I think I'll come back a little bit to spherical Bessel differential equation, which also you will come, you'll encounter quite a bit. So I'll sort of solutions of spherical Bessel differential.
Is that when
equation.
we had like the first kind and the second kind?
No. Remember when we do the Helmholtz equation in
Yeah,
spherical
in
coordinates?
Spherical cylindrical.
We do the one which we solved was the cylindrical coordinate system. When you get the Bessel differential equation, we got is but the one which is more common that you'll come across in quantum mechanics is the spherical Bessel differential equation rather than the other one. Okay, but it can be obtained from whatever we have. So I want you to have an understanding of that. So because that's more you'll encounter that more frequently than the Bessel differential equation we did in the class at the previous lecture. So I want to touch upon that a little bit more. Okay, I mean, so
Also, just one more question, regardless of the fact. I was confused when we can write this, when we can use the separation of variable thing in the partial differential equation.
right, that's also pretty deeper question actually. It is again, mathematicians can only answer that. So it has to be linear differential at least linear partial differential
Linear
equation.
partial
Yeah,
differential
but even, I mean, those are not easy to answer because it has even deeper, when is it applicable?
Mostly in physics we have encountered
We
linear
do that,
partial-
but we do, yeah. I don't think it's possible for non-linear partial differential equations. I don't think so. You cannot use the separation of variables, like solitons or something like that, solitary waves. Those are non-linear differential equations. So non-linear partial differential equations, you cannot do that. Yeah. So I mean, again, it's not trivial answer for those things. I mean, mathematicians must have even deeper reasoning for separation of variables method. I don't think it's okay. I have to give you your test paper, right? You didn't come last time. I have test.